Maybe tomorrow. We did sign up for the call.
Okay, so looking up here at our board, what I have here is our method for denoting that we're going to do a derivative. So this is taking the derivative of a function with x as the variable. So real quick, try some of these out. I'll give you just a little bit of time and then we'll go through them. If I were to take the derivative of each of these with x as my variable, so I've got x to the second, x to the first, x to the 0, x to the -1. So we got this little range of numbers hovering right around 0. So go through here and come up with a solve for the derivative of those. We're going to move on to the integration after that, and there's a reason for this progression. Okay, so using in red, again, this is my thought process. I'll put a little arrow going across here. So recall, we multiply out front with our exponent. So I have a 2. So I multiply by 2. The k is just a coefficient that remains. I have my variable x, and then we drop that exponent by a value of 1. So we literally subtract away 1. We get x to the first power. And typically, we don't bother writing down the first power. So we get 2kx. For this one here, again, I think about it as k to the first power. I multiply by 1, which is just kind of an invisible number there. K, x, I drop by a power of 1. That gives me x to the 0 power, which is another 1. So I get just k. This one here, my exponent is a 0. So I literally multiply by a 0, and I get 0. Think about what a derivative is. A derivative is actually the rate change. It's a version of slope. If I have a constant value k, I don't have any rate change, hence the 0. So it does make sense from a conceptual standpoint when you think about what a derivative represents. So here, instead of k over x, I think of it as kx to the negative first power. I'm going to multiply that out front. So I end up with a -1 times k. I take x and I drop it by a value of 1. So I get negative kx to the -2 power. And you can leave it like that. Typically what we like to do, though, is we like to show it as a positive exponent. So we just put it down below our division bar. And then this last one here is, again, just kind of showing us the trends. So I'm going to multiply by the -2. And then I'm going to bump it up to, I'm going to subtract 1 and get a power of -3. So I get a -2k x to the -3rd power. And so I would probably rewrite that personally as -2k over x cubed. And when we do derivatives, they're fairly straightforward. At least this type of derivative is fairly straightforward for us. Now when I come down here, what I'm going to do is I want to look at the integration. I've got all the same things, right? I've got x squared, x to the first, x to the 0, x to the -1, x to the negative. I've got all the same things. I want to look at taking the integration instead. So we've done that before, right? We do the integration where we do the opposite of the derivative. Derivative was multiply by the exponent and then drop it by a value of 1. Well, we do the opposite in opposite order. So we increase the power by 1 and we divide instead. So give those a shot if you want. What I'm going to do is I'm going to quite literally grab all these because it applies down here as well. Work. There we go. So we're just going to drag these down because I'm a cheater. I like doing shortcuts. So something like that. So I increase by a power of 1 and divide by that. So I'm going to increase this x squared to an x cubed and divide by that. So I end up with a 1/3. I have the letter k, which again is just a constant. I intentionally threw the k in there because I could have numbers in there. K could be 5. Okay, then it's 1/3 times 5. And then my x value has an increase this time. So I add the number 1 to my exponent and I get x cubed. All right, so I can continue here, bump this one up to a power of 2 and divide. So I get a 1/2. I get my coefficient. I have x. I'm going to bump that up to a power of 2. K is actually x to the 0 power, so I'm going to bump it up to a 1 and divide by 1. So I just get a k and an x to the first power. So I get kx. Now if I jump down here, I even have an x to the -3 down here. Again, I can see, I can see these trends. So if I start backward here, increase. So I literally take the number 1, add it to -3, and I get to the -2 power, and I divide by that. So I get a -1/2. That's dividing by a -2. I have the letter K. I have X. Add a 1 to the -3, and I get a -2. So I could write that out as K over 2x squared. And there is a negative term there because I had a negative exponent. All right, going up. I'm going to increase my power of -2 up to a value of -1 and divide. So I get a -k. I have x to the -1 power. And so I could rewrite that as -k over x. So if I have positive terms, I can do that. If I have negative terms, I can do the other. And what I've done is I've intentionally skipped 1. This one right here in the middle. What's the problem with this one? Increase the exponent by 1 and then divide by that exponent. What's my exponent going to end up being? 0. That's not a problem until we divide by 0. We dealt with 0 up here, and it wasn't a problem because it was multiplying by 0. We love multiplying by 0. It makes everything easy. Dividing by 0 gives us a value that is undefined. It doesn't give us a value. So this right here is a problem. This is like, comic book, I don't know what to do here. And so what we have to do is we have to go to our integration tables. We have to go through calculus and learn why this is true. I'm pretty sure back in high school, which was a long time ago, back in 1998/99, sitting in Mr. Kibbe's AP calculus class, I'm sure I learned how to do this and the reason behind it. And all I remember now is the answer. So all the steps leading up to it, I don't know. That's up to you and Mrs. Newsom. Me, I just use it. So coming down here, I am going to write down our statement here. The whole purpose of all of this, good practice, of course, is the following. When you take the integration of some coefficient possibly, maybe that coefficient is just the number 1, and I divide that by x, and I integrate that with x as my variable. Anytime I integrate, I have the ability to take any coefficient. So you know what? Let's bring the coefficient out front. We'll do our work, and then we just leave the coefficient. It just goes along for the ride, so to speak. So I end up with integration of, you could write it as 1 over x dx, but this is very commonly written as, and shown as, and thought as, said, spoken as, dx over x. That's x to the -1st power. That's where we increase the exponent to 0. It produces problems. And so what we do is you can literally go to our equation. We got this yellow equation sheet. I can literally go to the backside, and I've got all my calculus derivatives. I've got a bunch of integrations on there, and I can go to the list, and it shows me the integration of dx over x is the natural log of x. So that makes perfect sense. So this is something that's on your yellow sheet. This is something you would be expected to know for an AP exam, perhaps in May. And since we're dealing with natural logs, it's always useful to remind ourselves that if the natural log of randomly selected letter A is equal to randomly selected letter N, I can reverse the natural log process. If I go e to the A will equal, A would be equal to e to the nth power. We're going to use that when we do this integration. It is very common to use this knowledge of e and natural log.
Would it be k times the natural log of x, or do we just ignore k?
Oh, good point. Yes, I have neglected to include k. So let's slide that over. I forgot coefficient K. There we go. Thank you. So yes, so K is pulled out, but yes, it does have to go back in at the end. Right, so what we're going to do is we're going to use this a little bit later, because right now what we're going to do, and I'll have this saved and posted to our Google Classroom. So I'm going to skip forward here to make sure we get everything done in time. And what we're going to do is we are going to look at our next concept, and the next concept is going to be the drag force, sometimes referred to as air resistance, but we can do drag force through the water, call it water resistance if you want. We're going to do drag force. Once upon a time, you were a physics student, not to be confused with an AP physics student. And every single question, and we still do this to this day, is what happens when we drop something through the air? We talk about air resistance. We say, you know what? Let's keep this simple. Let's go with no drag. And we've been doing that all the time. We're still doing that. Just on this last test, you just did that. And what would happen is you draw yourself a little force diagram, and that was the only force. Back then, you were still using Fg instead of W for weight. We know that Fg could have been calculated by doing mg. We could have actually done, and we did, Newton's second law says that when you show all of your forces combined, and we only have one, that's going to give you your acceleration. So if I bring down mg, the masses cancel, and regardless of the size of our object, regardless of the mass, the surface area, anything, we say, you know what, if there's no air resistance, A equals G, 9.81, 10 when we do it in class for practice questions. And we just did two-dimensional stuff using this, right? So that's what we do all the time. And to be quite honest, we're going to continue to do that most of the time. Well, last year, what we did do is we, what happened right there, is we did, copy this one over here. We did branch out a little bit at the end of our force section, just like right now we're at the end of our force section. And we did branch out a little bit, and we said, you know what, let's add in a drag force, but let's keep it simple. Let's say it's a constant drag force. Now in class, students told me that the drag force is going to depend on how fast you're going. Because the drag force is quite literally how many air molecules you run into every second. Your object pushes on the air molecules. The air molecule has mass, which means it has inertia, which means that when you push the air molecule forward, it pushes you back. And if you run into 5 jillion air molecules, that's 5 jillion pushing back on you. Well, if I go twice as fast, maybe I run into 10 jillion air molecules in 1 second. Well, now I'm getting more force pushing back. And you told me as a class last year, it depends on how fast you're going. It depends on how big you are, right? The bigger I'm going to catch more air molecules. So we said, you know what, let's just keep it simple. Let's just say that it's a constant value, which means no matter how fast you're going, you get the same value. And then last year we called it F for force and D for drag. And we came down here and we could do our summation. There was actually an online question in my class that we had done. It involved someone jumping out of a building because there was a fire. What was their final velocity when they hit the big trampoline thing at the bottom? And you literally had to do a basic second law setup. What I find here is that because drag is taking away a little bit from our overall downward pull, we end up with an acceleration that's going to be a little less than g, but it still does remain as a constant. So maybe you had to calculate what that acceleration was, and maybe you calculated it to be 8.7 instead of 9.8. And you went through and did all the same stuff with just a different value. So those are the two things that we had done last year for drag. And now we are on to episode 3. If this is episode 1, this is episode 2, we're on to episode 3. And believe me, this is a series that has way more than 3 episodes. So by no means are we finishing all things drag in this class. There's lots of different types of drag. There's constants, there's Reynolds number, there's laminar drag, there's turbulent drag, there's all these different things. And so, you know, if you're going into aerospace, if you're going into cars, all those different things, anything that involves drag. You might work for the U.S. Olympic development team as a scientist who's trying to figure out the drag on a runner or on a swimmer. Could be anything. So what we're going to do is we are going to start a new slide, because now we're going to look at drag force as it relates, you know, a little more realistically. And that being that our drag force is going to vary with our speed. So the first thing that we always do is we always make sure that we have our little force diagram here. So I'm going to put in my arrows, and I'm going to switch over into our more commonly used letter, capital D for drag. I'm going to put in my gravity arrow. I'm going to call that W for weight. I can even throw on my mg. Some people call that downward arrow. They just call it mg. They skip W altogether. That's fine. And so now what we're going to do is we need to look at this. Say, okay, well, what are we going to do here? Well, we need a way to express drag. And so we are going to express drag as some kind of a function. That function is going to depend on how fast it's going, v. It also depends on other things like how big is it? What shape does it have? Is it going through air? Is it going through water? Is it going through jello? Is it going through whatever? Everyone always has that dream or that vision. What would it be like to dive into a swimming pool filled with jello? What would happen? I think that's probably just me. Maybe it's just me. I don't know. Anyway, so this K value here is going to represent, you know, we can call this lots of different things. We're going to call it, you can call it the drag coefficient. I'm going to call it the resistance coefficient. And what this does is this takes all of our constant values, all of our constant characteristics, and lumps them into one single term. So this might deal with the shape, some number that corresponds to the shape. It might correspond to our surface area. It'll be a number that corresponds to some kind of properties that we have for our fluid, viscosity and whatnot. And since none of these are going to change throughout the flight of our object, it's going to be a constant. Now, you will sometimes see this drag force represented with a negative sign out front. Why would it have a negative sign out front? I don't need a negative here in my picture because I got an arrow attached to it. But why would I have a negative sign? If a negative is a direction, why would I have a negative?
Gravity is considered positive.
Okay, so why the negative sign?
It's looking against it.
Okay, so think about the vectors I have in my equation here. Why the negative? K is just a constant, so D and V. Negative sign implies that they're opposites. Why is drag force and velocity, why are they opposite? Because they go in the opposite direction. In this case, it could be up. I can have a car driving sideways and have drag forces as well. Velocity and drag force are opposites. If I move to the right, drag pushes back to the left. It always opposes motion. So you might see it expressed as a negative sign. Up here, I don't bother with the negative because I just have my picture showing me everything. Right? So just like always, I do a summation. I do the sum of my forces equals, I have my weight going down, and I like having down as my positive term simply because my acceleration I like having positive. If I pull down, it accelerates down. I want them to have the same sign. So I'm going to subtract away this drag force, which is now going to be velocity dependent. And that's going to give us our MA. And you know, I came up here, I should have probably written this down. We are looking at a drag force that is velocity dependent. And again, this is finally a step in the right direction. There's still a lot of more complicated things to add to this, but this is a good start. And so I can take this equation, I can take it and run with it. We're going to do some high-level stuff with it here in just a little bit. But before we do that, let's go back and look at one last concept from last year. And that last concept here is the concept known as terminal velocity. No matter how complicated the drag function is, maybe there's a v squared in there or something, it's pretty complicated. No matter how complicated it gets, terminal velocity is usually pretty easy. Do we remember what terminal velocity is? Either what it is, why it happens, the conditions that it happens under, right? It is a value, it is a constant. When would an object have a constant velocity when in free fall? Gravity's always pulling it down, shouldn't it get faster and faster and faster? What has to happen for a constant velocity? The drag force has to equal and therefore cancel out our gravitational force. We have to have balanced forces. All constant velocities have balanced forces. How do we balance our force? Well, I can't shrink gravity. Drag's got to get bigger. How does drag get bigger? I go faster. So simple. I get so fast that the drag force equals the weight. So for our terminal velocity, it is when our weight mg is actually equal to our kv, because acceleration is 0. So quite literally, I take this equation here and I put in a 0. So mg and kv are equal. So if I wanted to solve for my velocity, I simply, well, solve for my velocity. I get an mg, I get divided by k. And again, no matter how complicated this kv equation could become, all I have to do is solve for v, and that's just a simple algebraic step. So I can figure out my terminal velocity. Can you ever have a drag force bigger than gravity? Gravity down, huge drag force going up. Can you have an upward acceleration when you're in free fall? And upward acceleration is going to do one of two things, right? It's either going to make you go up faster and faster and faster, and that doesn't make sense. Throw something up in the air and immediately get slower. What's another upward acceleration? What outcome could I have? Slowing down when I'm traveling which way? Down. Downward velocity, slowing down would give me an upward acceleration. Is there ever a time where I'm in free fall where I start to slow down? When? Parachute. If I'm falling down, I'm going 100 miles an hour, and all of a sudden I open up this big bed sheet above me. I just increased my area huge. I'm still going 100 miles an hour. I get this huge upward drag force. I can have an unbalanced force up. What does that thing do? Unbalanced force slows me down. The slowing of my speed decreases my drag force. And just like that, my drag force shrinks right back down to the original size we had before. Whether I'm skydiving at 100 miles an hour or floating gently with my parachute opened 10 miles per hour, I have the same drag force for each. I either have a huge velocity in a small area or a huge area in a small velocity. Right, so we need to get to a point where we can solve. So we can do all of this. I want a way to solve for v based on time. I jump out of a plane. I know the air that I'm traveling through. I know my size. I know everything. How fast am I going to be going after 5 seconds, after 10 seconds? I don't even have time in here right now, so we need to go through our steps. And what I want to do is one last slide, and these are the steps to solve for velocity as a function of time. I'm going to give you the steps that would be required on an AP test to get full credit. Number 1, pretty common to be asked to draw a force diagram. And they expect sizes to be proportional. So if it's terminal velocity, they want arrows the same size. If it's not terminal velocity, they'd probably expect the drag force to be a little bit smaller. Number 2, the whole purpose of all force diagrams is to get to a summation. So that's going to be step 2. Step 2 is come up with a summation. And we recognize that's going to be gravity down, it's going to be drag force up, and that's going to give us an acceleration. Number 3. Number 3 is going to be to substitute in V as often as possible. How could I get V into the equation any more than I already have? There's my equation sitting there. How can I get V in there any more? It's already there. Can I replace any other variable with something that has V in it? Mass seems to be kind of standalone on its own. I don't think mass is going to work. Our gravitational acceleration, that's a constant value, so there's no sense in taking that out. K is a constant involving the objects involved. The only other letter is A. How can I get A out and V in? How can I express A? Acceleration is? What's our definition for acceleration? Change of velocity per time, right? The rate change. Let's do the calculus version. There we go. Our acceleration is dv over dt. So I'm going to quite literally put that in. So we get mg minus kv equals m. I take out a acceleration and put in dv over dt. That's just a calculus version of delta d and delta t. So now, 5 steps. We're on to step number 4. Step number 4. I've got 2 variables. I've got v and t. I want to solve v in terms of t. I'm just about done here. So what I want to do is solve for dt. I want dt moved over on its own. So it looks like I can multiply dt over and divide by this big thing here. And so I end up with dt is equal to, I have m dv on top. On the bottom, I've got mg minus kv. And at this point, step 5 is basically do the math. Integrate. So what I do is quite literally, I'm going to just take this, I'm going to move it down here, and all I do is put in our little integration symbol. I do this, and I do this, and the one thing that we haven't done yet with integration is I need to be told, okay, I know what I'm doing here. These little symbols here, it means add up all the small pieces. Well, how many small pieces do I add up? And so what we have is something called limits. A limit is basically being told, where do you start? We're going to start at time equals 0, and we're going to end when time is equal to t, from 0 to t. Over here, our velocity, we're going to drop this thing from rest, so we're going to start with a velocity of 0, and we're going to end when velocity is v. And now what we can do is we can go through and do our integration. Adding up all the small parts of t is easy. Take up t, break it up in a bunch of parts, add them all together, and I get t. This right-hand side is the tough stuff. I see a dv, and I see a v. I'm thinking natural law. All right, I went over time a little bit. I apologize. But now we are ready to go. I have made a second video, a part 2, that shows just this, just how to go through and do the integration. And that's going to be an asynchronous, view it alone kind of a video.